Hey everybody, this is the second of a two-lecture series on what it means for a function to be well-defined. As we saw in the last lecture, we gave some very nice examples where everything works the way it should. Today we'll talk about cases where things don't work the way they should and figure out what that criterion is that makes it work. Let's remember what we showed last time. Let's pick n, and let's consider the equivalence relation where we look at things mod n. In other words, x is equivalent to y if and only if x is equivalent to y modulo n. This is an equivalence relation, as we've shown before. We therefore get equivalence classes, and then we showed that if we define plus sub n and times sub n as addition and multiplication modulo n, this very much respects these equivalence classes, specifically the equivalence class corresponding to x plus the equivalence class corresponding to y is another equivalence class, and it's nice to see that it's the equivalence class corresponding to x plus y modulo n. Okay, if we think about this in a more concrete case, think of the evens and odds when we do modulo 2, we know that even plus odd is another way of saying that the equivalence class corresponding to 0 plus the equivalence class corresponding to 1 is the equivalence class corresponding to 1. What we showed last time, and what it means for this operation to be well-defined, means something like the following. Let's say somebody said, what is even plus odd equal to? And we've forgotten. We know that even plus odd should be something, but we just don't know which one it is. So here's how it works. Pick any even number, say 6. Pick any odd number, say 3. 6 plus 3 is 9, and that's odd. From that it follows that even plus odd is odd because addition mod 2 respects these equivalence classes. So again, by choosing one representative of each class, we can get the general formula for all the elements in one shot. Now this is one of those situations where it works so well that we can almost convince ourselves how could it ever be any other way. But let me show you how special this really is. Let's think of a general context in which we have a set x, and on x we can define some sort of addition. That is to say, any two elements of x and y, x plus y is well defined and it's another element of x. Right? So for example, if x is the integers or the naturals, we know how to add things. Take any two subsets of x, a and b, and let us define a plus b. The sum of the two sets a plus b is we look at all sums of pairs of elements where we take the first one from a and the second one from b. This is known as the addition of sets. Of course we can do this, but we don't know what's going to happen. Now, let's imagine that we have a partition of the set x. Let's say we have some sets a1, a2, all the way up to ak, and these form a partition. Is it always true that if we take, say, a1 plus a2, that gives us some other set in the partition? The answer is no, okay? In fact, it rarely is. Only in certain special cases does it actually work. So that's one special fact that addition modulo n has that general partitions don't have. So to be more concrete, let me come up with an example where this does not work. So take the natural numbers, for example. Let's let S be the set of perfect squares inside the natural numbers. So specifically the set 1, 4, 9, 16, and so on. Let's let T be all the natural numbers that are not perfect squares. So for example, 2, 3, 5, 6, 7, 8, 10, and so forth. Now check, this is clearly a partition, right? Every natural number is either a perfect square or it's not. Specifically, the union of S and T is the naturals, the intersection of S and T is the empty set. So what is S plus S? Specifically, what do we get if we take the set of all perfect squares and add it to the set of all perfect squares? What do we get? So notice, let's take two perfect squares. Let's take 9 and 16. Well, 9 plus 16 is 25. So sometimes we can add two perfect squares to get a perfect square. 9 plus 25 is 34, and that's not a perfect square. So sometimes we can add two perfect squares and get something that's not a perfect square. So notice here is that we do not have s plus s equals s, nor do we have s plus s equals t. In fact, s plus s is just some sort of complicated set that has nothing to do with s and t. But remember, when the partition comes from mod n, right? So for example, if n equals 5, if I take the two sets, equivalence class corresponding to 4 and equivalence class corresponding to 3, I can add those two sets by saying take 4 and 3. 4 plus 3 is 7. 7 is equivalent to 2. Therefore, the class according to 4 and the class corresponding to 3 is the class corresponding to 2. So two things are true. Number one, the addition respects the partition in a certain way. If I take any two sets in the partition and I add them, I get another set in the partition. And something even nicer is true, is that we can figure out which set we get by choosing a representative on both sides. That's actually quite special. Okay, now we're in a position to really formalize what we mean by well-defined. So here's the definition. Let X be a set. Let's assume we have an equivalence relation on X. And let's take X modulo that equivalence relation to be the partition generated by the equivalence classes of the equivalence relation. Now let's let f be any function with domain x. So specifically, f goes from x to a, where a is some other set. Let's now try to define f tilde, which is a function whose domain is the equivalence classes, as follows. Let's define f tilde of the equivalence class corresponding to x as just f of x. Okay, we're trying to do that. Does that actually make sense? Well, it doesn't always, but we say that f tilde is well defined if whenever x and y belong to the same equivalence class, then f tilde of x equals f tilde of y. Said another way, we need f to respect the equivalence relation in the following way. Whenever x is equivalent to y, we need that f of x be equivalent to f of y. But note, this may or may not be true, depending on the situation. We have a couple of examples. Let's take the integers and take n equals 5 and look at the equivalence relation mod 5. So we're really talking about the ring Z5, as we talked about before. Let's take the function f of x equals x squared. So let's say that x is equivalent to y, which means x equals y mod 5. Then, as we proved a long time ago in the fundamental theorem of modular arithmetic, x squared is equivalent to y squared modulo 5. So what we've proved is that if x is equivalent to y, then f of x is equivalent to f of y. So this thing is a well-defined function. However, let's see an example where it doesn't work. Let's go back to x is the natural numbers, and let's go back to this partition we had where we take the squares, call that set S, and we take the numbers that are not perfect squares, call that set T. That is a partition. What's the equivalence relation corresponding to that partition? Remember, the way we can move from partitions to equivalence relations is we say two elements are equivalent if they live in the same set inside the partition. Specifically, we have that x is equivalent to y if and only if x and y are both perfect squares or both not perfect squares. And we say x is not equivalent to y if one of them is a perfect square and the other one is not. Okay, that gives us an equivalence relation. We have our equivalence classes. Now here's a function. F of x is x plus 3. That's a perfectly valid function. And let's check. F of 1 is 4. F of 4 is 7. So notice, even though 1 is equivalent to 4, they're both perfect squares, f of 1 is not equivalent to f of 4, because 4 is a perfect square and 7 is not. Here's another example of something we might do. Let's try to write down a function from z4 to z6. Right, so that's the integers modulo 4 to the integers modulo 6, where we just take f of x to be x. Is that a well-defined function? Well, let's compute. So f of x is x. So in z6, f of 2 is 2, because it's 2 mod 6, but f of 6 is 0. But in z4, 2 and 6 are equivalent. So we get a situation where on the left-hand side, we have two numbers that live in the same equivalence class, but when we apply f to them, they now live in different equivalence classes. So this is not a well-defined function from z4 to z6. Okay, so we just talked about functions, but remember the thing we talked about originally in this lecture was we talked about addition. And addition's not quite a function, right, because it takes two arguments. But notice we can do all the same stuff that we just did before. So for example, let's say we have a set x, and let's say we have any function of two variables, right? F of x, y, of course, its domain is now x cross x, and goes into some set A. And here's what we need. We need that when x1 is equivalent to x2 and y1 is equivalent to y2, we need that f of x1, y1 is equal to f of x2, y2 inside the set A. So one example that works, remember, is Zn. If we have x equals x prime and y equals y prime modulo n, then x plus y is equivalent to x prime plus y prime modulo n. So addition is well defined there, as we've shown before. But again, let's say we take the set, the natural numbers, where we take the partition S and T, remember the perfect squares and the non-perfect squares. And what we just saw is 9 plus 16 is 25, but 9 plus 25 is 34. Therefore, 9 is equivalent to 9 by reflexivity. 16 is equivalent to 25 by the fact that they're both perfect squares. But 25 is not equivalent to 34 because one is a perfect square and one is not. Therefore, this addition is not well defined. In summary, the point I really want to make here is that When we take the set Zn, where we look at equivalence classes modulo n, it works so well with addition and with multiplication that we might think, this just always works. And it really doesn't. Only in certain cases, when we have this nice fact that equivalent inputs give rise to equivalent outputs, do we have a well-defined function. I'll stop there.